Well, one of the reasons is that this Grover algorithm is a very important algorithm. It touches very important things of quantum parallelism. So it's good to sort of stay with it for a while. So let us sort of, we will discuss a few points on this, but before that let us sort of recapitulate the main points once more. So, yes, once more. So you remember the thing that someone, Alice wants to know, Alice knows the phone number of someone. She does not want to call that person. Call person without knowing the person's name. Yes, so this was the scenario that we know the phone number of someone whose name she doesn't know or remember, something like this. This was the scenario that we discussed. So she gets hold of a telephone directory, having n entries, and these entries are in alphabetical order of the names, and not serial number with respect to the phone numbers. Yes, so otherwise it would have been simple, but this is as in usual directories. So on average she needs to look at n by 2 entries. Yes, this was the classical case. And then we set up a quantum version of it. The quantum formulation. The quantum formulation was considered as the so-called black box, which we know is a quantum mechanical operator, but we don't know how it works. If we feed it with something, it will give out something in a quantum mechanical way. But feeding the black box with something and getting something out is considered equivalent to looking at the directory once. This is the point. So this black box is to be considered in the quantum formulation as the telephone directory in the classical case, and looking at the directory once is like feeding the black box with an input and getting the result once. So it is known that this black box acts as like this. This is gives y and minus y, depending on whether this y is y0 or not. Yes. So we had set it up like this, that if some ay is 0 and if some ay is equal to 1 and this ay equal to 1 if and only if y is equal to y naught and ay equal to 0 if y not equal to, it's like this. And then we considered this two things. There was the xi and there was the v. Yes, this xi was the sum of all the input states. So these this y0 has to be, in the quantum scenario, has to be thought of as equivalent to this person's name, this name of the person that Alice wants to find, and the other y's that are not y0 are the names of the other person, the other n minus 1 entries. And then we assume that this xi is 1 over root n summation over I, y, this. This also contains this y naught, but I don't know what is y naught, but I know what is xi, because this entire set I know. I don't know which element of the set I want, but I know the set. So in principle, I can create that superposition. This can be difficult in practice. And there was this V, which was this identity minus this, and the U was actually identity minus this. This U is given to me, this thing is given, and these two I assume that I can prepare. Does not require knowledge of y naught. Yes, this one requires knowledge, but this is given to me. And there is a restricted use, so I will count by my that number of times I use u will be compared with this n by 2. And then we did the geometry of these reflections and so on, and we landed on a number that was root n. Yes, we saw that we could go, we could do the problem with root n queries. Yes. This query is a standard word. It means using n, using u. Yeah. So a query in the classical case is looking at the directory once. Fine. This was what we did, and so you are sort of encouraged to ask difficult questions to Grover, well, difficult in the sense which may seem difficult to us, it may not be difficult to Grover. So let us enumerate what type of questions we may ask. So this, well, I have put some, you can tell more. We have discussed some of these the last day. So, for example, the first one can be, this one we have discussed many times. How am I going to create U if I don't know y naught or y naught? This is the number, this is the vector. Well, this we have discussed before. Yes, this is we are not going to create U. U be given to us. You have to think of it as the telephone directory. Yes, this we have discussed before. Well, the item B also we discussed a little is that why am I given the telephone directory in the quantum case as this and not this. Well, I think we have discussed this before as well. This is, you understand the question? So we have, in the quantum case, we have assumed that the directory, well, the directory is the names, and then we have encoded those names in a set of orthogonal states, and then we have assumed that we have been given a state like this. This is the xi that we have been given. Yes, we have, or we can create that state out of that directory. This is what we have assumed. So this is the directory that we have got. This and the U. This is, and then we create for ourselves the V. So how come it's given like this and not this? And of course, will it work if I use this and not this?
How is that second, the mixed state?
It's a mixed state. Yes, it's.
How is it useful?
Pardon?
That is not useful at all because it will take a case of some state with yet operating this density matrix on some other y naught. You'll get the same y naught. Right?
Pardon? Once more.
If you have a pure state y naught.
If you have the pure state one now.
And you are applying this operator 1 by n y naught on that state y naught, you'll get the same state y naught again. That will not be useful.
Once more, I didn't understand. You mean you take this state and you apply it on what?
On some state, you are having a state ray.
Well, this is the state that I am given. This is the state, this is not the operator.
Okay.
This is the quantum state. The quantum state is a mixed quantum state, this is a pure quantum state. So if you, this is written in pure form, if you write it in density matrix operator, you will get this term, but you will also get the cross terms. Yes? So the question is, so actually this is the classical case. So in the classical case, you are essentially, so you can think of the classical case as a register where you have many systems. The first one is 1, the second one is 2, and so on. Or you can assume that when you choose one at random out of it, it's actually something like this. Yes, it's like you have a box which has n balls, each of them marked 1 to up to n, and then you to take one of them out without looking at it, and then the state that you have is this. Yes, you are. So this corresponds to looking at a random point in the classical directory. Yes. So the question is whether one can use this to do the quantum problem. So I don't know whether. Pardon?
This is just white noise.
This is white noise in the sense, if you think of it as white noise. Noise is usually considered from outside.
No, I'm saying that sigma y is just identity.
This is the identity operator on the entire space. Exactly.
Purely random.
This is purely random.
Identity of operator state. No, we'll have no information on that.
So with respect to y naught, this one and this one is not so different.
But we need an initial state which contains information on all the states.
So this, in that sense, both are the same.
No, that has no information on any state.
What do you mean by that? That has no information. It is a given. It is a valid state.
No, we are trying to do a reflection and in the end reach minus y naught
This is
by
true.
multiple reflections. So that state is useful in the sense we know its initial position with respect to y naught in some sense.
So
know
we
how
also
it-
know the initial position of this with respect to y naught. So it's in some hyperdimensional. It's not a block sphere. So thinking of a block sphere in higher dimension is difficult. But suppose we can. So this state is at the center of that block sphere. This state is at some point here, and the y naught is anywhere here. You don't know where that is. We don't know the position of y naught with respect to this.
Yes.
And similarly, we don't know the position of y naught with respect to this.
But how will it get reflected? This state. About
So,
the-
it will not be reflected in the way that we have done before, but it will be reflected in some way. If it's a mixed state, so there is a more complicated way to reflect it.
But how? No, in the sense that how do we construct a reflection out of this state?
Yeah. So, the concept of reflection we considered only when there are pure inputs. So, I don't even know how to consider reflections for mixed states. But certainly, one can do evolutions with mixed states.
Or the identity?
So, when you actually do this experimentally, this thing you will never get. You will get something mixed with some noise. So that will be somewhere, instead of being there, it will be somewhere there. It will not be at the middle, but it will be somewhere there. So mixed states are not so bad.
That state is mixed state is fine, but if it would have been a pure row of that only side, then it would have been useful. But it's a mixed state with no information, like identity.
No, so
random.
this word, no information in sense of what? This is a valid quantum state, just like this. And with respect to y naught, this and this is the same. There are n terms in the superposition. You don't know which one is y naught. It's the same thing here.
But no information of anything, any of the states.
Yeah, like if we apply U to that.
No, what do you mean no information? It is a valid state. You should not say it is
But
a.
it has no unique information of any y prime.
So it does not have any information about any pure state.
any.
But a valid, completely random noise is a valid quantum state.
Yeah.
So with respect to Y naught, which I don't know completely, these two states are not different, they are the same.
But like in the end, we want to reach somewhere, reach to some particular state, and
Exactly.
if we apply any unitary operator on this state, we won't get anywhere. It is purely random. So
It's purely random.
So any unitary operator on this state will not lead us to anywhere.
That is not clear. Why should you? I will apply, I may have to apply, I mean, it is certainly possible to read the classical directory. So you can think of reading it n times, by reading n by 2 times with this state, we can go to the answer. And this is exactly what we do in the classical case.
So it may not be as good as the growth, but we should be able to do the algorithm, and the efficiency should be n by 2. I mean, at least n by 2.
No, and we do it.
Yeah,
The
we
classical
should be
model
able
is
to do
like,
it.
like that. In the
Yeah.
classical case, we actually do that. We keep on doing the measurements, and we keep on removing one of the terms one by one, and we go to n by, on average we reach there. You make measurements all the time, but you will need n by 2 times to do that on average.
So we should be able to write a mathematical consistent framework, like what we
Yeah,
do for
yeah, and-
classical, we should be able to write it.
And you just keep on doing measurements. So
Yeah,
in the classical case,
algorithm is different. The point is, the state is not useless. It will not be useful for a quantum advantage, but it is not useless.
It's
As you are
not even
saying.
a quantum mechanical description of the algorithm then, because you will keep
No,
on
why?
reducing the rank of your
Might as
operator.
exactly.
So
Then
writing
it's
the
not
language
a-
of what we know as a
No, but
That no, we already know all classical algorithms can already be implemented in quantum state. That is not at all anything new. I mean, in the sense that
yeah, that is what I'm saying. So this is the classical state.
yeah,
And if you work with it n by 2 times, you will reach the classical answer.
no, that is fair. That is just following the classical algorithm
Exactly.
itself.
No one is
Word to
claiming
word.
that we give any quantum advantage.
The question is, why have I been given this telephone directory like this?
I find this question genuine. I was thinking the telephone directory has classical indeterminacy, it has all these names. So why the telephone directory can be written in a superposition of all these states?
Yes,
Quantum
so
indeterminacy.
the point is, the point what I want to make here is that this state and this state are both blind with respect to Y naught.
Yeah.
They have the same mathematical status or even the physical status with respect to the state Y naught. However, it is this that works and this that does not. This is what I want to say. And it's the quantum parallelism that works. It's the superposition of the entire thing. Here the superposition is not there. The off-diagonal terms are missing. That is the thing that
They
is.
are different with respect to Y naught. Their
They're
projection
not.
to Y naught is different, right? Like if you take a like
There,
that has a
in the
1/2
sense that it
tensor.
does not have any information about Y naught. This is the thing. In that sense, of course, there are different states. So if you project them, it will give you different states.
Exactly. It will give you different
It will
quantum numbers.
give you
That
different
is what
answers.
qualifies as information in the sense.
No, it does not have any information with respect to Y naught. Both of them. This is what I want to say. So actually you can deal with more states like this. So if you, let's say you take this state, you take a projector of that with some probability P and mix it with this. This also does not have any information about the state 1. And actually in the noisy versions of this Grover algorithm, it is this one that you should actually consider. I mean, this is a very simple type of noise. Realistic noise will never be white, it will be colored, but let's see.
Yet get an advantage.
Pardon?
Yet get an advantage even if you start with something like this.
I don't know. I guess some people must have done this before. I have not done. Number C is that if operators that is machines, given to me, this U that is given to me, can be functions of y naught or y naught, why can't I just project xi to 1? Yes? So we have been given a unitary operator that depends on y naught. I don't know what is inside there, but why am I given that? Why am I not given a projector? I mean, I'll just project it there and get the answer. Well, I don't know the answer clearly. So actually, again, my difference with Arun Pati with respect to his paper was somehow related to this, a little different. So my answer in this case will be that the probability to succeed will be mod square, yes, which is 1 by n, and it tends to 0 as n tends to infinity. This is one problem, and I'm also not sure whether this, because you see, this projecting to this is the operation that we are talking about. This operation, I'm not sure whether that can be considered as a black box. This I am not very sure. So I would request you to think more about it. I am not. So the thing is that I don't know the answer clearly. So this is what I told to Arun as well. So
in all quantum algorithms, don't we consider black boxes to act unitarily? Almost always.
I would say yes. I haven't seen any example where black boxes has become. Pardon?
So projections aren't even allowed.
No. Just because until now it has not been considered as having no projection is a valid quantum mechanical operation. Only it's probabilistic.
No, when you say the probability to succeed will be 1 over root 10, that means you are performing a general measurement.
On the side.
And you are saying that it is the probability that it will collapse to the state that we want is 1 over n.
Exactly.
But if you construct a projector, a physical measurement device that will specifically shoot out y naught, it will always shoot out y naught.
No. Look, but whatever black box you give, it has to be quantum mechanically valid.
So you're saying y naught is valid, right?
So, but y naught deterministically is not a valid operation.
Because?
This is not a valid operation, right? How will you use this operation? The only deterministic operations valid in quantum mechanics are unitary operations. Projection operations are measurements. So along with that y naught, you will have that entire class of other operations to which it will also project.
No, all the requirement I assume was it's Hermitian. It should, if that's enough, I'll be able to physically realize it, right?
No, Hermitian is the Hamiltonian. It's e power IH that is realizable. H is not realizable. Deterministic operations in quantum. So once more, so this was why we discussed on the first day. The first was quantum statics. You described quantum state. The second was quantum dynamics. Quantum dynamics is deterministic, but the only operations that are allowed are unitary operations. You can add an auxiliary system, consider a unitary operation on the whole thing, and then trace out the auxiliary system. This will lead you to non-Hermitian dynamics in the local part that will still be deterministic. you get these Markovian, non-Markovian, Lindblad evolutions and all this. But on the whole, it is always unitary. And that is the only evolution that is allowed, deterministic. The other thing, the other way you can change a quantum system is by measurement. And that is not deterministic, that is probabilistic. You don't know. So this was the third postulate that we discussed, the quantum measurement. We said that you can measure on a basis or on chunks of basis. You can have higher order projectors, higher rank projectors. And then there are definite, and which one will click in a particular case is completely random, unless it is orthogonal to it, then it will never click, or it is inside its rank, then it will always click. But if there is a non-zero probability in the Born rule, then it is completely random. In a given run, you don't ever know how it is going to occur. It's postulated. And the probability that it will occur is the Born rule. And then you get projectors as valid operations, but then the projector also has other things along with it. So the black box will be such that you can feed in the xi, and you will sometimes get the y naught out, but it has a very low probability of clicking. And you have a marked y naught. So the telephone company has marked it that if something comes out here, that is the y naught, but it has a very low probability of coming.
Sir, can we consider this projection like, suppose we are sending unpolarized light, and then we have a Nikon prism or anything with its axis parallel to some detection that we want, and then that unpolarized light will always come out through the Nikon prism aligned in that direction.
But it never comes out always. It comes with a lesser intensity. So if you send in photons one by one, it will sometimes not come, sometimes come.
So you're saying if we consider the projector y naught,
Exactly.
since
So,
it is not unitary,
yeah, so it is not deterministic. That is very clear.
so to make it unitary we need other projectors
No,
also
no, no.
along
You
with
can never make a projector unitary. I mean, you can make it into a complete measurement. And then it becomes a valid operation in the sense a valid way to change a quantum state.
Okay.
You have to consider the other projectors so that the whole sum will give you the identity on the relevant space. And then you can do the measurement. But then you don't change the probability with which this clicks. And the state that you can create here is either it will not contain any information about the y naught, so you can consider the superposition, for example, or you can consider the mixture, and you will always get that 1 by n as your answer. But I mean, I'm not sure. I mean, this is a question that I made up. Okay, I mean, I have never worked on Grover algorithm, so I'm not sure whether this is a stupid question or something. So it's like, so something that I don't know is, can project to y naught black box. Be a black box. Because I mean, it is probabilistic first of all, and maybe other things, I don't know. I mean,
So at the end, even in Grover's algorithm, we need to measure the eigenvalue of y naught to get what y naught actually is. Otherwise, we even after producing a y naught state, we won't know whether it has been produced.
exactly.
So we need to measure the eigenvalue. Here we can't even do that.
No, you measure in the y basis, which contains the y naught.
But how do we get the eigenvalue?
Eigenvalue. You don't need the eigenvalue.
Otherwise,
The
how do we-
answer is given by whether the y naught clicks.
But
and-
we don't know the y naught, right?
But in the Grover algorithm, after you apply it this n by 2 times, root n times, you will always get y naught.
Yeah.
With
but
very high probability.
After getting that y naught, we still don't know what y naught is. I mean, it's
No,
a
no.
quantum state in some particle.
No. You have to assume that you know the directory. So you know what is 1, what is 2, what is 3 up to n. And these are already correlated with whoever, Bob 1, Bob 2, and so on. And there is a y naught somewhere, and this Bob y naught, this is known.
Yeah. So we need to
Now
pass
when
that
you
y naught
measure in, and this is the thing, and then you write down this, and there is a Y naught here, and there is this.
Yeah, but
Then at the end, this thing clicks, this register is already there.
yeah, we need to pass the state into this register.
So these names are there, you write down these numbers, you create these create a system which has these quantum states as options.
Yes.
Then you create a state like this in that system. You don't create all of them. You create one state which has all this in one superposition. And then you apply this, what it was, UV, right? Or VU, I don't remember. This was UV, n by root n times. And then at the end, you make a measurement in this basis. And whatever clicks, you go back to the register, you get Y naught here, you go back to Bob Y naught, you go and
So
get the name.
it will come into some input state, will come into some output state Y naught. We still don't know what that Y naught is yet, and we need to pass it on to this directory again.
You have to come to this directory.
That
And-
is somehow a measurement only.
That is a measurement in the sense, but you have to just look, I mean, that is like,
I mean, you can
you
give
already
it back
know
to the
what that
company.
number is,
Yeah,
right?
I mean, you don't have to do it yourself, you can give it to the company or something.
Yeah, I mean, so
They
we
have
have,
some record, but
Exactly,
they eventually measure some conjugate moment or sort of like eigenvalue they'll find out.
oh,
They have some machine
yeah, I
that gives
mean,
them
you
the-
can, yeah, you can call this as the eigenvalue of that operator.
So they have some machine that
That-
input a state and you get.
So that
what
register is already there. I am not considering the time required to look at that. That will also require some time.
What the point is that can't be, I don't think how that can be done here. If you project it onto Y naught, you'll just get that.
Yeah, exactly. You will get that same Y naught, and you come here directly and look at this.
But if you had that Y naught projected measurement, you already had the eigenvalue.
But if predictive measurement.
Yeah. You have a box in which you always give out it tells you when the Y naught outcome comes out. That one it tells you. So that box was not available to you before. In the previous instance, you had the U available and a measurement onto this available. Now, instead of this, you have another box available, and there is, and all these are, so this is a measurement on this basis, such that in all the other instances, it is dumped. In all the other instances, it is dumped. In this case, it gives output. This is prepared by the telephone company. So, telephone company knows which Bob I am trying to find out, just like the previous case, the U knew about the Y naught. I did not know, but the company knew Y naught. In this case also, the company knows what the Y naught is, so it gives you a machine in which this is the one that comes out, and all the others are dumped. But it will click with a very low probability. This is the problem.
So why is it important that you be a black box?
No, I mean, I'm just trying to set up the quantum problem, quantum version of the classical looking at the directory. So, it's essentially, this entire algorithm is essentially trying to do a tomography of the U. So, it's like a process tomography in some sense. Process tomography is actually used for something more complicated, something that is not a unitary, even non-unitary operations they use. But this is a unitary process tomography that we are trying to do here.
What is tomography?
Pardon?
What is tomography?
Tomography means trying to find. So, tomography was first used for states. So, there was state tomography, which means trying to find out what a given state is by doing measurements. And then a process tomography is, it says that you have a machine that takes input and gives you output, and you want to describe that. That is a process tomography. But that can actually also be non-unitary. Yes? Yes, so as I said, I mean, I still don't understand this question clearly. Still thinking. So, so the last question that I wrote here is more, again, I don't know whether that is a valid question. So is as you people have been asking also, so why do we agree with Grover that applying U once is equivalent to opening the telephone directory once. So applying U once in the quantum case equivalent to opening the telephone directory in the classical case once. Yeah. So the answer is I don't know. I mean, the point is that people seem to agree with him.
It is something that can be pre-prepared, right? In the sense that Xi and V are common for everyone.
Xi and V are common for everyone.
The company can initially, for all numbers, create U1, U2, UN, and then based on the person who seeks some numbers corresponding eigenvalue, they can give them the corresponding U, so that they can apply this algorithm themselves.
But it's like when when Alice goes to the company knows who the boyfriend of this girl is, but won't tell her. But give her this.
They won't store all the information.
Yeah, exactly. So this is the situation that is. But yeah. So as I said, I don't understand this completely. Probably it's again not a. It's okay. I mean, probably the correspondence is okay, but I'm just not tell my feelings, thoughts. Yeah, so I don't have any other questions left. If you want to ask more questions, you're welcome. To me or Robert.
There's a systems engineering question. Like you said, we can do superposition using interference.
Pardon?
You can do in superposition using interference experiment. How do people do this on lattice or not? Full atom superposition.
You mean how they create superpositions? I don't know. How they create it.
So can you say that the superfluid is the superposed state of all the atoms in the lattice?
Yeah. I mean, the point is that it's not really it's a phase transition of the system, and then the ground state is created in some state in which they can actually prepare it well, and then they change the parameter of the system, some sort of a field, and system phase transits into the other model in which they get into all the systems. But then it's just creating the superposition is not enough. You have to have individual access to all the lattice site, and that becomes difficult because to have access in the sense you want to rotate those individual, you want to act on those individual sites. That involves shining lasers on each of them, and then that tends to disturb the system not clear how to use an optical lattice in a quantum computer in an efficient way. And there are some bottlenecks as of now. Okay, so we will end with Grover algorithm today. And go to something else. So,
Sir, what is the physical significance of line V?
physical in, you mean, I mean, in case
What's
of
the
the,
role of V basically?
so the role is essentially that it will lead you to why not in root n steps. You mean to, what does it mean by V? It's a reflection with respect to the xi, or something perpendicular to xi on the plane of y naught and xi.